Everyone, we are Group 9. Let's introduce our group project. I believe many people, when they were in their freshman year in NTU, had experience in, or at least heard of that your department was going to hold a summer camp for high school students, like these Instagram accounts presents. And here comes a problem for the organizer who wants to recruit the workers for the job. It's a personnel allocation and matching problem because each person has different skills and we need to match them to the right job based on what each position needs. Besides this, we also need to consider what is best for the camp versus what is best for each person. We could decompose the problem into four parts. First, we have applicants. Each applicant has their personal information like biological gender, study year, experience in the camp, preference order. Second, we have 7 different departments. Like every department requires its team to possess certain attributes, such as academic. It requires an experienced senior as leader of the team due to the complexity of the work. And additionally, every department must include at least one junior member so that institutional knowledge and camp culture can be passed on to the future generations. Third, we allow applicants to take on 2 roles at the same time. However, we need to make sure the workload is manageable so it does not affect the quality of their work. There are 2 phases of the camp, before camp and during the camp. If someone has 2 roles, they should not be overloaded in the same phase for both roles. Fourth, organizer aims to staff all departments at their optimal size while satisfying all stated requirements, seeks to maximize the overall satisfaction of the assigned staff and minimize the unrecruited member of people. And these 3 elements consist the objective function we would mention. In the formulation part, overall we define 3 sets: applicants, departments, and time phases. Within the department sets, we also define subsets for positions that require a leader, senior member, or junior member. For applicant related parameters, we use the 4 attributes introduced earlier: biological gender, study year, prior camp experience, and preference order. Except for the preference order, all of these parameters are binary. A smaller preference order means the applicant prefers that role more. From the organizer's perspective, the ideal case is for each department to be staffed exactly at its optimal size. In practice, this is not always possible. So we allow a small deviation by introducing upper and lower bounds for some departments. And the variable BJT indicates whether department J is busy during the time phase T. And the weights W1, 2, 3 control the 3 key components of the objective function. They sum to 1.
Next, we introduce our decision variables. We first introduce 3 types of binary variables. Xij indicates whether applicant I is assigned to department J. Rij indicates whether applicant I is selected as the leader of department J. And Vi indicates whether applicant I is recruited. Then, we introduce Gj plus and Gj minus as non-negative integer variables, representing the difference between the actual staffing size and the optimal staffing size of of department J. GJ plus is positive if and only if the actual size is larger, and GJ minus is positive if and only if the actual size is smaller. Our objective function is consisted of three terms, with weights W1, W2, and W3 respectively. The first term stands for the staffing gap. The second term stands for the preference order. If an applicant is assigned a job he or she isn't preferred, the penalty of this term will become bigger. And the third term stands for the number of people not recruited. Now, we introduce our constraints. This page shows constraint on definition and sizes. By definition, GJ plus and GJ minus stands for staffing gap, VI stands for unrecruitment. And the third constraint is our size requirements, that is, systemic size must be within allowed bounds. This page shows constraints on seniority. First, team and structure is restricted to juniors only, and at least one junior and senior per department in JS and JR respectively. This page shows constraints on gender. We need at least one male and female in services, and exactly 10 males and 10 females in team instructor. This page shows constraints on leader. We need exactly one leader per department in JL. A leader must be assigned to their department, by definition. A leader must be senior, have prior camp experience, and cannot hold a concurrent assignment. This page shows constraints on loading. Each applicant is assigned to at most 2 departments, and no concurrent busy assignment across phases. Lastly, constraint on domains. Xij, Rij, and Vij are binary variables, and Gj plus, Gj minus are non-negative integers.
In this session, I will introduce our heuristic algorithm for the staff recruitment and allocation problem. The goal of the algorithm is to quickly construct a feasible staffing plan while achieving a good overall solution quality. The key idea is simple. First, we satisfy the most restrictive constraints to guarantee feasibility. Then we gradually improve the solution by selecting assignments that provide the greatest improvement in the objective function. This allows us to obtain high-quality solutions in a short computation time. Our heuristic consists of 2 phases. Phase 1 focuses on feasible solution construction. During this phase, we construct a feasible solution that satisfies all the constraints. Phase 2 focuses on objective improvement. In this phase, we iteratively improve the assignment quality while maintaining the feasibility. In phase 1, we satisfy the most restrictive constraints first. We assign leader positions because they need senior and experienced applicants. These positions are the hardest to fill. Next, we satisfy the instructor department's gender and junior quotas. Then, we handle the service department gender requirement, followed by senior and junior requirements in other departments. Finally, we assign the remaining applicants until minimum staffing requirements are satisfied. This ordering guarantees a feasible solution whenever an instance is feasible. For each allocation step during phase 1 and phase 2, we consider all feasible assignment candidates. For each possible assignment, we calculate the change in the objective value denoted by delta. The candidate with the smallest delta is selected. since it contributes the greatest reduction in the objective value. If multiple candidates yield the same delta, we use their preference priorities as the tie-breaking rule. After obtaining a feasible solution in phase 1, we enter the improvement phase. We check all feasible applicant department pairs and calculate their corresponding delta value. Then selected the one that produces the greatest improvement in the objective value. This process is repeated until the remaining smallest data is larger than or equal to 0, meaning that no remaining move can further decrease the objective value. In this way, the solution gradually converges to a locally optimal assignment. Finally, let's briefly discuss the time complexity of our heuristic. The main computational bottleneck lies in the improvement phase. To put it simply, the algorithm performs at most 2n-5 assignment iterations, where n is the number of applicants. During each iteration, all feasible applicant department pairs are evaluated, which is up to 7n pairs in our problem setting. Therefore, the overall complexity is big O n squared, which is polynomial and remains computationally efficient for large instances.
Next, we will explain how our data is collected and generated. Our data contains 3 parts: department, applicants, and weighting. Constraints about department, that is, requirements for each department, are drawn directly from NTU CSIE camp. Applicants' information is randomly generated based on scenarios that closely reflect actual camp recruitment. For weighting, we set W2 to 0.858 and W1 and W3 much smaller. Huge W2 is for balancing the marginal effect of the 3 factors. We consider 4 factors in the applicant composition to generate data: numbers of applicants, preference concentration, proportion of experienced seniors, and gender balance. By considering the above 4 factors, we design 6 scenarios. S0 is a base case, where all factors are normal. S1 stands for high competition, that is, there is some department that everyone wants to go to. S2 stands for leader shortage. S3 is for gender imbalance. S4 is applicant shortage, and S5 is applicant excess.
Let's look about the performance evaluation. And since the recruiting problem is not typically large in scale, we could use Groby optimizers as the lower bound of our benchmark. So Groby optimizer will provide the optimal solution to the problem. We use the heuristic solution to compare with the Groby optimizer provide solution as the optimality gap. And in addition, we have an upper bound. The upper bound is considered to satisfy one of the 3 factors, exactly one of the 3 factors in the objective function. So you could see the objective function at the below of this page. So for first term is the optimal size. We randomly assign to matches the optimal department size and to let the applicants randomly assign to department until the department is full. Second, we have to minimize the preference satisfaction. It means that we allocate the applicants based on their first choice preference departments. And if the department has reached its capacity, we randomly choose one of the left applicants and to go to his second or more preference order choice. And so for last is the unrecruited minimization. It means that applicants are randomly allocated across departments under the constraints that no individuals holds more than one position. Thereby, we can maximizing the total number of recruiting applicants. So here is our results. So for each scenario, the summary stats is shown in this table. We could see that in the optimality gap parts, the average optimality gap across all scenarios from the base scenario and to the 1 to 5th scenario we have designed in that section. Across all scenarios, the optimality gap is below 7%, so it is quite good. And the heuristic algorithm is very closely approximates the optimal solution. And however, there are one of the scenario 4, the optimality gap reach more close to 7%. It is one of the worst. And so the reason is that the security for applicants creates a significantly tighter feasible region here. So in the phase 1 of our heuristic, it would have a more impact on the objective value, and when it comes to phase 2, utilized doing local improvements to recover from early choice is fewer available. So for the improvements from the upper bound benchmarks, there are 20 something to 30 something % improvements from this benchmark into our heuristic algorithm. Is also quite good. Here we could see the results from the heuristic algorithm and 3 benchmarks as upper bound. So we could see the optimality gap for the green part is the heuristic. So the optimality gap from the green part is very good from 6 scenarios. And for benchmarks, there are like 40% to 60% optimality gap. So the performance of our heuristic is quite good. So the last, we have the conclusion of our reports. First, we review the main things to our project. In this project, we model the staff recruitments and allocate the problem into an integer program. And we design a heuristic algorithm that run less time than the Groby optimizer, and it provides nearly results from the optimal solution. And to evaluate it, we evaluate across the real-world data and 6 design scenarios. So the heuristic algorithm achieves an average optimality gap below 7%, and it also outperforms in all benchmarks. It shows that the proposed algorithm produces a near optimal solution, which is efficiently and make it as a viable tool for camp organizer to facing other complex or multi-constraint recruitment decisions, even not a camp for a high school student, even for a camp for like the whole society. So we also have some future works need to improve in this project. The first one is that we only consider the preference for the one applicant itself, but we didn't consider the preference for applicants with applicants. Like 2 or 3 applicants may want to form in a group and go into the same departments, and we didn't consider it here in this project. So this is maybe needs to be considered for a general camp organizer. So the second part is that the 3 factors designed in the objective function is now the same importance with each other. And one improvement way may be we could let the organizer to choose ways to mean the importance of each factor by themselves. It could let the organizer to choose like whether one of the 3 factors or even other factors are more important than other one. So for last but not least, incorporating the real applicants data from the past camps or from the future camps would allow us to better scenario design and more realistic performance evaluation rather than the 5 scenarios we design now. And we want to use more real-world data to use in this program and let the heuristic algorithm design better in the future. So this is the end of our report, and very thanks for your listening.